All right, this is the answer key for the review packet for winter break. I'm going to go ahead and try to squeeze 4, 5, and 6 under this video, and I'll make separate videos for the other questions. We have a rocket that weighs 1,000 newtons. So that would be 1,000 newtons of force of gravity. Experiences thrust from a rocket of 3,000. Okay, so that would be an up force of 3,000. How long will it take this rocket to travel 500 meters? So this is a multiple part problem. Basically, we want to know a displacement of 500 meters. And we want to, so what are we going to need to know? The acceleration of the rocket, the initial velocity of the rocket, the final velocity of the rocket, the time of the rocket. That's what we want to know. We can just assume it starts from rest because it didn't tell us and it should have. So we need another thing. The other thing we're going to need is the acceleration. And to find the acceleration, we're going to use the net force. The net force is equal to mass times acceleration. The net force is 2,000 newtons because there's 3,000 up and 1,000 down. And that's equal to the mass. The mass is 100, right? Because force of gravity is related to the mass times acceleration due to gravity. We're just going to use G equals 10 because we're big boys now and girls times A. Right, so that 100 will cancel that 100, so acceleration is equal to 20 meters per second squared. The rest of the problem is just uniform accelerated motion. You've got to pick an equation. I'm going to go with x equals 1 v naught t plus 1/2 at squared. If we assume the initial velocity was 0, which we have to, otherwise, I don't know, maybe there's another way to do it, but we're probably right. I think I'm just going to let you finish it from there. You can do the math. 500 equals 10 t squared. 50 equals t squared. I think, can you pick it up from there? Take the square root of both sides. That's about 7, right? Because the square root of 49 is 7. The square root of 50 is about 7. All right. The next question, unfortunately, is at the bottom of the page, so that was not good. We have a mass that slides up a ramp. The angle for the ramp is 28. The 3 kilogram mass is, connected to a second mass. Oh, brother. Oh, here's a drawing. Okay, so what a mess. The 3 kilogram mass is on the ramp, and the angle is 28. And the 3 kilogram mass is connected to 3.25 here. Okay. Now, frictionless pulley, woohoo! Coefficient of friction, there is a friction here though. Mu is that. You find the acceleration, the kinetic energy after it's traveled 25 centimeters up the ramp. Ooh. Okay. So what we need to do is start with a free body diagram. This is a free body diagram question. This has got a force of gravity of 30 newtons, and this has got a force of gravity of 32.5 newtons. You can ask me how I know that, and I'll tell you. There's a tension pulling this way, and a tension pulling that way, which are going to cancel each other. If the pulley is massless and frictionless, the tensions cancel. We have a normal force here, and we have, and that's it. Oh no, we have a friction force here. All right, so the acceleration is going to be equal to, oh no, that was all off camera. I'm so sorry. Here, let's go ahead and pause the video and take a look at the picture and see what I did there with the free body diagrams. Oh my God. So this is going to be equal to the net force over the mass of the system. The mass of the system is 6.25 kilograms. So we have to use the free body diagram to find the net force of the system in the plane of motion. The forces we have going up the ramp, we have 32.5 newtons. That one is pulling up the ramp. The tensions, as we said, canceled. This is there's a component of this guy that's trying to pull it down the ramp, and that's the sine component, so minus 30 sine 28. Also the force of friction. Right, and that's equal to the net force, which is what we want for right here. So now we need to find the force of friction. The force of friction is equal to the normal force times the coefficient of friction, and the normal force is equal to the cosine component of the force of gravity here of this thing, right? It's got two components. One component is adjacent to the angle and it's balancing the normal force, and the other component is trying to pull the block down the ramp. So 30 times cosine of 28 times, this is not on, 30 times cosine 28 times 0.285. So this is 7.5. And 30 times the sine of 28 is 14. And this is still 32.5 newtons. So plus 7.5 minus 32.5. And so the net force is 10.9 newtons. 10.9 newtons. So we have 10.9 divided by 6.25. Oops. 1.7, and I get a 1.7 meters per second squared for the acceleration. The kinetic energy after it's traveled 25 centimeters up the ramp. So there's a couple of ways to do this. One way we could do it is we could solve for the final acceleration after 25 centimeters. So we could say x equals 0.25 meters, and the initial velocity is 0, and we don't know the time, but we do know the acceleration. It's 1.7. And we could solve for VF using UAM, or we could use the work energy theorem, which says, I don't know, that might be a little tricky. We'd have to figure out how much work is done going up the ramp. I guess that would be the net work done. So we do know the net force, and we know the displacement, so I guess we could do that. We could say 10.9 newtons, that's the net force, times 0.25 meters, that's the displacement. That's the work, and that's equal to the change in kinetic energy, and since we're starting from rest, that would be the kinetic energy. So that is, if you do it this other way, you would go 1/2 times the mass, which is 6. Oh no, just 3, because it's just that one, times this VF squared. You would have to solve for VF using UAM, which would be b squared equals b naught squared plus 2ax. All right, let's leave it at that. How are we doing on time? 8 minutes. Ugh. All right, we have a ball suspended from the ceiling of a room by 2 cords shown in the drawing. The ceiling is 2.2 meters above the deck. The angle theta is 61 degrees. The other cord is perfectly horizontal. Find the tension in both strings. All right, so I'm just going to redraw this over here. This is 61 degrees. So this has got 2 components. It's pulling up, and it's also pulling sideways. And then the other cord, I really wish I had another color, is pulling this way, right? So we're going to call this one T2 and this one T1. Notice that it's not moving. So the net force in any direction is 0. Free body diagram. Also, there's a force of gravity here of 31.2 newtons. So you can see that this, if this is 61, this is 61, alternate interior angles. And so this x component here is going to be equal to T2. And this y component here is going to be equal to 31.2. It's the only, so Ty is equal to 31.2, and that's equal to the sine component. It's equal to T1 sine of 61. So T1, the angle-y one, is equal to 31.2 divided by the sine of 61. And Tx is equal to T1 times the cosine of 61, and that's equal to T2. So once you figure out this, you can put it here and multiply it by the cosine of 61 and get your answer for T2. The potential energy of the ball relative to the deck would be the mass, 3.12, times g, times the height, 2.2 meters. And you multiply that all together and get the answer. All right, there you have it. Now I got to go watch a football game.